Hello and welcome to Math World, the world where difficult math is a very easy one. So today, dear friends, we are going to speak about arithmetic sequences, and we are going to solve the top 5 hardest exercises in arithmetic sequences that were presented in different exam papers. So if you are ready, let's start. Exercise 1. Evaluate the sum of the expression 2n plus 1 when n goes from 1 to 100. The idea in this exercise is to analyze the expression 2n plus 1. So let's denote the expression 2n plus 1 by u sub n. So u sub n equals to 2n plus 1. Next, we will show that, in fact, u sub n is an arithmetic sequence. So it is an arithmetic sequence. For this, we will use the definition of arithmetic sequence, and we will prove that the difference of any two consecutive numbers is constant. So we'll show that if we take in general two consecutive numbers, for example u sub n plus 1, and we subtract u sub n, then we'll always get the same constant, which in fact this constant is the common difference of our arithmetic sequence. So let's start proving this. U sub n plus 1 will be equal to, so I'll remember you that for finding u sub n plus 1 we have to replace in the formula of u sub n with n plus 1, and we will get that u sub n plus 1 is equal to 2 multiplied by n plus 1 and plus 1, which gives us 2n plus 3. Next, let's find the difference between u sub n plus 1 and u sub n, which is equal to 2n plus 3 minus 2n plus 1, which gives us 2, and it is a constant. So we proved that the sequence u sub n equal to 2n plus 1 is an arithmetic sequence with the common difference d equal to 2. And in fact, our exercise is to evaluate u sub 1 plus u sub 2 plus u sub 3 plus so on till u sub 100. So we have to find the sum of the first 100 terms of our arithmetic sequence. We know that the formula for the first n terms of an arithmetic sequence is n divided by 2 u sub 1 plus n minus 1 multiplied by d. So in our exercise, for evaluating S100, we have that S sub 100 is equal to 100 divided by 2 multiplied to 2 u sub 1 plus 100 minus 1 multiplied by 2, the common difference, which will give 50 multiplied by 2. Now, for finding the value of u sub 1, we replace n with 1 in the general formula. So when we're replacing n by 1, we'll get 2 multiplied with 1 plus 1, which is 3. So u sub 1 is 3 plus 98 multiplied with 2, which gives us the final answer, 10,200. So the answer to this question is 10,200. Next, let's move to the second exercise. The second exercise tells us the following, that we have the sum of the first n terms of the sequence is s sub n equal to 3n squared plus 11n, all divided by 2. And we're asked to find the nth term of this sequence and then to prove that the sequence is an arithmetic one. So, what do we have here? We have this Sn is equal to 3n squared plus 11n, all divided by 2. So, to find the formula for the nth term, this means to find u sub n, having the formula for the sum of the first n terms, we need to remember that u sub 1 is equal to s sub n minus s sub n minus 1. We proved this identity in the previous lesson from our math world, which was called the sequences. So in that lesson you can find how this formula is proved. Next, we are going to find s sub n minus 1. So s sub n minus 1 will be equal to, so we have to replace in this formula n with n minus 1 and this n with n minus 1, and we will obtain 3 n minus 1 squared plus 11 n minus 1 divided by 2. If we open the bracket, we will obtain 3 n squared plus 3 minus 6n plus 11n minus 11, all divided by 2, which gives us 3n squared plus 5n minus 8 over 2. So let's go back to our expression for finding u sub 1. So replacing s sub n with its formula, we'll obtain 3n squared plus 11n over 2 minus, replacing s sub n minus 1 with its formula, so we will obtain 3n squared plus 5n minus 8 over 2. We have the difference of two fractions, so we'll obtain 3n squared plus 11n minus 3n squared minus 5n plus 8 over 2, which gives us 6n plus 8 over 2, or 3n plus 4. So we proved that, or we found that u sub 1 is equal to 3n plus 4. And next we can move to point B, where we have to prove that the sequence is an arithmetic one. So for this we just have to show that the difference of any two consecutive numbers is a constant one. So we have to show in general that u sub n plus 1 minus u sub n is a constant. Having u sub n, we will find the formula for u sub n plus 1. So we will replace n with n plus 1, and we will obtain 3n plus 1 plus 4, which gives us 3n plus 7. And next, the difference of u sub n plus 1 minus u sub n will be equal to 3n plus 7 minus 3n plus 4, which is equal to 3, that's a constant. So because the difference of any two consecutive numbers is constant, this means that our sequence is an arithmetic sequence, and we proved the think that u sub 1 is an arithmetic sequence. So this was the exercise number 2. Let's move to exercise number 3. In exercise number 3, we have the following. The nth term of an arithmetic sequence is given by the formula u sub 1 equals to pn plus q. If u sub 2 is equal to minus 1, u sub 9 is equal to 20, and s sub n is equal to an squared plus bn, find the values of a, b, p, and q. So, the idea in this exercise is to start with the information that u sub 2 is equal to minus 1 and u sub 9 is equal to 20, and to find the values firstly for p and q, having that u sub n is equal to pn plus q. Because u sub n is the formula for the nth term, using this formula we will find the formula for u sub 2 and u sub 9. u sub 2 will be equal to p multiplied by 2 plus q, which is 2p plus q, and u sub 9 will be p multiplied by 9 plus q, which is 9p plus q. So from the condition we had that u sub 2 is equal to minus 1, from the nth term we obtained that u sub 2 is equal to 2p plus q, so we obtained that 2p plus q must be equal to minus 1. Because u sub 9 is equal to 20, and at the same time u sub 9 is equal to 9p plus q, we obtain that 9p plus q must be equal to 20. And we have to solve this system of simultaneous equation. So, if we analyze the tentative system, we see that in the both equations we have plus q. So if we subtract, for example, from the second equation the first equation, we will obtain that 7p is equal to 21. P is equal to 3. Having the value for p, we going back in one of the previous equation. I will go back to the first equation, and we'll replace p with 3, so we get 2 multiplied by 3 plus q is equal to minus 1, which gives us that q is equal to minus 7. And this gives us that u sub 1 is equal to 3n minus 7. And we found the value for p and q. Next, we are going to find the values of a and b. For this, we will use the information that this arithmetic sequence has the formula for the sum of the n terms equals to an squared plus bn. From the theory of arithmetic sequences, we know that the sum of the nth term of an arithmetic sequence is equal to n plus 2 multiplied by 2 u sub 1 plus n minus 1 multiplied by d. And now let's use the fact that un has the formula 3n minus 7 and deduce the formula for s sub n. For this, we will find u sub 1, which gives us 3 multiplied by 1 minus 7, which is minus 4. Now, we have to find the common difference. For this, we just have to take the difference of any two consecutive numbers. So because we have u sub 1 and u sub 2, so d will be equal to the difference between u sub 2 minus u sub 1, and it is equal to minus 1 minus 4, which is 3. So, having u sub 1 having d, we obtain that by formula Sn is equal to n divided by 2 minus 8 plus n minus 1 multiplied by 3, which will be equal to n divided by 2 minus 8 plus 3n minus 3, or n over the 2, 3n minus 11. So we have, or let's expand a little bit, it will be 3n squared minus 11n all over the 2, or 3 over the 2n squared minus 11 over the 2n. So, from one side, S sub n is equal to an squared plus bn. From another side, the same S sub n is equal to 3 over the 2n squared minus 11 over the 2n. Because we are speaking about the same S sub 1, this means that a is equal to 1.5 or 3 divided by 2, and b is equal to minus 11 over the 2, minus 5.5. So this is the final answer to this exercise. So we found the value of a equal to 3 over the 2, the value of b minus 11 over the 2, the value of b equal to 3, and the value of q equal to minus 7. So let's move to the next exercise. Exercise number 4. In exercise number 4, we have that a, b, and c are consecutive terms of an arithmetic sequence, and we have to prove that 1 over square root of b plus square root of c, then 1 over square root of c plus square root of a, and 1 over square root of a plus square root of b are also consecutive terms of an arithmetic sequence. The idea in this exercise is to use the fact that if a, b, and c are consecutive terms of an arithmetic sequence, this means that the difference of two consecutive terms is a constant. So a minus b is equal to b minus c, which is equivalent to the fact that b minus a is equal to c minus b, which is equivalent with the fact that 2b is equal to a plus c. So, in order to prove that these three terms are also consecutive terms of an arithmetic sequence, we have to prove one of this equality. I will choose to prove the equality that 2 multiplied with the middle term, so 1 over the square root of c plus the square root of a, is equal to the term 1 over the square root of b plus the square root of c plus the term 1 over the square root of a plus the square root of b. What we're going to do next, we are going to rationalize the denominator of each fraction. So for the first fraction, we have to amplify with the square root of c minus the square root of a. The second fraction we have to multiply by the square root of b minus the square root of c. And the third to multiply with the square root of a minus the square root of b. So we have to prove that 2 square root of c minus the square root of a over c minus a is equal to the square root of b minus the square root of c over the b minus c plus the square root of a minus the square root of b over a minus b. So next, because on each denominator we have c minus a, b minus c, a minus b, this implies that c minus a is different from 0, equivalent that a is different from c, b minus c is different from 0, equivalent that b is different from c, and a minus b is different from 0, which is equivalent that a is different from b. So a, b, and c are different terms. They have different values. Sorry. Next, because b minus c is equal to a minus b, we will replace b minus c with a minus b. And we have the following form, that 2 square root of c minus square root of a over the c minus a is equal to, we have to prove that this is equal to the square root of b minus the square root of c over a minus b plus the square root of a minus the square root of b over a minus b. But the right side of this expression is the sum of two fractions, and we'll obtain that the values for the right side is the square root of a minus the square root of c. So we have to prove that 2 the square root of c minus the square root of a over the c minus a is equal to the square root of a minus the square root of c over a minus b. Because on the left hand we have the square root of c minus the square root of a, and on the right hand we have the square root of a minus the square root of c, we will write it in the form 2 the square root of c minus the square root of a over the c minus a. We have to prove that this is equal to the square root of c minus the square root of a over the b minus a. So we inverse these two terms. Now we can divide both sides of this expression by the square root of c minus the square root of a, and we know for sure that this is different from 0, because a is different from c. Divided by the square root of c minus the square root of a, we have to prove that 2 over the c minus a is equal to 1 over b minus a. If we multiply both sides by c minus a, b minus a, which for sure we know that it's different from 0, we have to prove that 2 multiplied by b minus a is equal to c minus a, or 2b minus 2a is equal to c minus a, or 2b is equal to c plus a. But this last expression is true because a, b, and c are consecutive terms of an arithmetic sequence, and we have that 2b is equal to a plus c. So all our steps of the demonstration, we use the information that a is different from c, b is different from c, and a is different from b. In case that a is equal to c is equal to b, this means that we have a constant sequence. For example, a, and in case that a is equal to b is equal to c, then we have for sure that the terms 1 over the square root of b plus the square root of c will have the form 1 over 2 the square root of a. The second term will be the same, 1 over the square root of 2 square root of a, and the third 1 over 2 the square root of a, which for sure is also a constant sequence, which is an arithmetic sequence. So in this way we proved exercise number 4. Now let's move to exercise number 5. In exercise number 5, we have the following. We have the sum of the first n terms of an arithmetic sequence is given by the formula S sub n is equal to n plus 1 over 2. And we have to evaluate the square root of S sub n plus S sub n plus 1 and minus u sub n. For evaluating this expression, firstly we need to find the formula for S sub n plus 1 and to find the formula for u sub n. I will go back to the formula for S sub 1 and I will expand it, so we will obtain n squared plus n over 2. For finding the formula for S sub n plus 1, we are going back to our formula of S sub n and we are replacing n by n plus 1 here and this n by n plus 1. So we will obtain n plus 1 multiplied by m plus 1 plus 1 over 2, which is n plus 1 multiplied by n plus 2, and if we expand, we will obtain n squared plus 2n plus n plus 3n plus 2 over 2. Now, having Sn plus 1 and having Sn, we can find u sub 1. U sub 1, as you know, it is the difference between Sn and Sn minus 1. So we have to do one more step to find S sub n minus 1. But S sub n minus 1, it will give us n minus 1 multiplied by n over 2, which if we expand is n squared minus n over 2. So now we can find the formula for u sub 1. So it will be n squared plus n over 2 minus n squared minus n over 2, which gives us n squared plus n minus n squared plus n over 2, or it is equal to n. So now we have all the components to evaluate our expression. So our expression has the form S sub 1 plus S sub 1 plus 1 minus u sub 1, which is equal to the square root of n squared plus n over 2 plus n squared plus 3n plus 2 over 2 and minus n. Now let's make some calculation that are present in the square root. So we'll have the square root of n squared plus n squared plus 3n plus 2 over 2 and minus n, which is equal to 2n squared plus 4n plus 2 over 2 minus n, which is equal to n squared plus 2n plus 1 minus n. If we analyze it into the expression n squared plus 2n plus 1, it is n plus 1 squared. So we have the square root of n plus 1 squared minus n, which is the absolute value of n plus 1 minus 1. But because n is a natural number n plus 1 for sure is more than 0, and the absolute value of n plus 1 will be n plus 1 minus 1 is 1. So the final answer is 1. So the expression that we had to evaluate is equal to 1. And this was the last exercise of our presentation. So you saw the top 5 hardest exercises from the arithmetic sequence that we have presented in different exam papers. At this point, dear friends, I want to tell you thank you very much for your attention. And as always, please like this video, share this video with your friends, and don't forget to subscribe to our channel to see another amazing and interesting themes in mathematics. And once again, remember that in math world, the difficult mathematics is a very simple one. Thank you again, and good luck to you.